All right, in this example, we're talking about cholera, which is an intestinal disease caused by the cholera bacteria that multiplies exponentially. We are actually given an equation to work with in this example, so that's helpful, and it is the equation for relative exponential growth or continuous exponential growth, where we have the base of e. We're told that time is representing hours. We're told we're starting with 2, and we're just asked how long to get to 10. So I want to fill in these numbers into this formula. So P of t is population at some point in time, so that's the 10. And then P0 is the starting amount, and it told us if we start with 2. So our base this time is e, exponent 1.386t. So most of this problem is similar to what we've been doing with both the doubling time and half-life models, but it is a little bit different having a base of e. First difference is that our exponent is a multiplication problem instead of a division problem. However, we start the algebra the same way. We have this initial amount of 2, and we'd like to move it away from our base, so we'll divide by 2 on both sides. Sorry there. I have 5 equals these 2's cancels, and so I have e with an exponent of 1.386t. Now, like the other problems I've done, I have a variable in my exponent, and so I want to use a logarithm on both sides. However, because my base is e, I want to use a logarithm that has a base of e rather than a base of 10. And the logarithm that I want to use is called natural log. The natural logarithm is abbreviated ln. So like the common logarithm, I will write it on both sides. So I'm going to have the natural log of 5 is equal to the natural log of e with an exponent of 1.386t. So this ln that I've used on both sides is for natural log, and I want to find the key on my calculator that has ln and type ln 5. So when I do that, I get 1.6094, and again, we'll use at least 4 digits when we're working with logarithms. On this side, just like I've done before, this exponent gets multiplied by the logarithm due to the product property of exponents. So 1.386t is multiplied by the natural log of e. So in order to figure this out, I need to figure out what is the decimal for natural log e. So I have 1.6094 is equal to 1.386t times. So to put this in my calculator, I'll type natural log, then I'll type second and use the natural log button to get the e. The calculator will prompt me to type an exponent, so I'll type an exponent of 1, hit enter. All that work will lead me to that this value is 1. Well, now I know that multiplying by 1 is the same as having the original number, so I can rewrite this, and I have over here 1.386t. And so what I have happen here is because I use natural logarithm with the natural base of e, and that value was 1, the truth of the matter is that this is a true inverse and truly simplifies to 1 or cancels itself out. And so the purpose of using the natural logarithm rather than the common log like we did on the others is because it really simplifies the math, and I only have one step left. So I'll divide on both sides by 1.386. This side, these cancel out, and so I'm left with t. On this side, I'll place this in my calculator, and I got an answer 1.16, and it would continue with the decimal, and the question up here is talking about time in hours, so this is hours. We talked about with our very first example that there is not a rounding rule, so just follow directions on your homework. So you might end up rounding that to 1 hour, 1.2 hours, etc. What we see is that it does not take the cholera bacteria long at all to go from 2 bacteria to 10 bacteria, but approximately an hour, just slightly longer. We're going to do a second example of this type of problem, and it also includes cholera. So give me a moment here to switch to the next slide. So we're keeping the same general information, that we have the same formula. This time, however, we're asked, what is the doubling time for cholera? So doubling with time would be the time it takes to be twice as much. If I think back to my previous example, I had P of t, which we had put in 10 because we were asked how long does it take to get to 10. And we had a starting amount of 2 bacteria, and we had the rest of our equation. So I can use this 2 again, but I don't have to. The most important thing that I do here as I fill in numbers is that I take this concept of doubling into account. So if I use 2, the bacteria is to double, so that means my population, I want to find out how long is it going to take for those 2 bacteria to become 4 bacteria. Now, I used the 2 because it was previously in the problem, but I truly could have made up any number because I could have started with 10, and then I would be asking how long would it take to get to 20. Or I could have started with 5 over here and ask how long does it take to get to 10. The key is that whatever I put for my starting population, I want to double it because I'm asked to figure out how long does it take to double. Now, to do my math, I'll divide by 2 on both sides. These guys cancel. Here I have 2 equals e with an exponent of 1.386t. Because of the e, I'll use the natural log on both sides. On the left-hand side, I'll type natural log of 2 into my calculator, and that gave me 0.6931. And again, we're using at least 4 digits in that decimal. On the right-hand side, this exponent moves to the front. This becomes multiplication, 1.386t times the natural log of e. As we experimented with and tried on our calculator last time, natural log of e simplifies to just be 1. And so when I multiply something by 1, this equation simplifies to 0.6931 equal to 1.386t. So I honestly think the problems that have the e as the base are a little bit easier than the first ones we did where we had a 2 or a 0.5 as a base, because there we're having to use a little bit more algebra to finish up. Here we just have 1 step remaining and we want to get t by itself, so I'll divide both sides by 1.386. On this side they do cancel and I'm left with t equals. On this side, I'll type this into my calculator, and when I did that, it's not exact, but it's incredibly close to 0.5. And time was in hours, so basically it takes a half an hour for the cholera bacteria to double.